thank the organizers for putting together this meeting and, well, giving me the opportunity to speak. It's a tremendous honor. So like everybody else, I owe Rodney a great debt of gratitude for his central role in creating and cultivating a beautiful area in theoretical physics. And as we have seen this week, this area remains both fascinating and very vibrant. So now I had the pleasure of meeting Rodney a few times in my career, and he always was extremely kind. One of these meetings was in Cairns in Australia in 2010, and I have very fond memories of this. And one of my memories is I managed to persuade two of my heroes to pose together for this photo here. Now, what I want to talk about has a certain relation to the things Giuseppe was talking about. So it's about matrix elements in energy eigenstates of local operators in integrable models. And the motivation for doing this work comes from generic many-particle systems. So these are systems with local Hamiltonians, but no conservation laws. And there, it's known and it's established now, there is a very profound relation between the structure of local operators in the basis of energy eigenstates and the relaxation of observables to equilibrium after driving them out of equilibrium or initializing the system in some non-equilibrium initial state. So more precisely, what I will be considering is matrix elements of some local operator, especially local operator in energy eigenstates. So these objects I call here O and M. And these are, of course, very complicated objects. So the thing I'm interested in is the probability distribution function of these matrix elements. And in this generic case I have described here, so these are known to fulfill the eigenstate thermalization hypothesis. And in particular, they're known to be all exponentially small when En is not equal to Em. Now, generic models have a particularly simple structure of energy eigenstates. So here is a sketch of what things look like for, let's say, a non-integrable lattice model of spins, but with a Hamiltonian that has a local density. So the axis is just energy density because it's a lattice model. There is a minimal energy density, so that corresponds to the ground state. There's a maximal energy density, which corresponds to ground state sector of minus the Hamiltonian. And the states at these edges of the spectrum, so they're lowly entangled and they're very different in nature from the energy eigenstates in the middle of the spectrum, so at finite energy densities. So their typical states are all locally thermal and fulfill the eigenstate thermalization hypothesis. And in addition, there can be rare states which are non-thermal and are known as scars. Now, what I will try to address is what is the analog of this story for generic models in the integrable case. So more precisely, what is the probability distribution function of these matrix elements of local operators in integrable models? And I will focus on a particular example because it's the simplest integrable model in many ways, which is the repulsive Lieb-Leninger model. So it's just non-relativistic bosons with a point-like interaction. And this interaction parameter here I take to be positive. And the reason for that is That makes it particularly simple because there are no bound states in the model, so no string solutions to Bethe-Ansatz equations. Okay, so now in contrast to generic models, which I started with, integrable models have, as everybody knows here, have conservation laws, which have densities that are spatially local, and they commute with the Hamiltonian, commute with one another. And the presence of such local conservation laws immediately changes the structure of energy eigenstates in a fundamental way compared to generic models. Okay, so this is the same picture I just had for a generic system where only energy is conserved. Now, if I fix the energy density to somehow be in the middle between the ground state and the maximal energy state, I still can have thermal states there. So these are eigenstates which locally, for any local measurement, look thermal. And the overwhelming majority of states are thermal states. So these are the most likely states. And their number is just proportional to the exponent of the thermal entropy at the temperature I'm considering, corresponding to the energy density I've fixed. But at the same energy density, I can, of course, also have non-thermal states, which I obtain by now fixing not just the energy density, but also some or all of the densities of the other conservation laws, which I can fix to non-thermal values. So this gives me what I call atypical states. They can be described by so-called generalized Gibbs ensembles. These are much rarer than the thermal states by construction, but there's still exponentially many of them. And these are very important for non-equilibrium evolution in integrable systems. Okay, so now these atypical states or thermal states, we will use this as an organizing principle for studying the statistics of matrix elements. But before coming to that, we should first briefly recall what energy eigenstates look like in the Lieb-Lininger model or integrable models more general. So Lieb-Lininger model is solvable by Bethe-Ansatz. So that gives us simultaneous eigenstates of all the conservation laws, which I can label by rapidity variables. So now in the Lieb-Lininger model, particle number is conserved. I have a U1 symmetry, which means I can fix the particle number, let's say capital to be capital N. And then these states which have Bethe-Ansatz form are eigenstates of the Hamiltonian and all the other conservation laws. These rapidity variables, which parameterize the eigenstates, fulfill some quantization conditions if I impose periodic boundary conditions, which I'm doing for the purposes of this talk. And these quantization conditions are, of course, just the Bethe equations. So they are these coupled nonlinear equations, which I have written in their logarithmic form, where they involve these integer or half-odd integer numbers ij, coming from just taking the logarithm of the non-logarithmic form of the Bethe-Ansatz equations. And I'm sure, as everybody knows here, so the story is if I specify a set of these integer or half-odd integer numbers, then I can solve these Bethe equations. That gives me a set of rapidities, and these I can plug into the expression of the wave function. That gives me then the eigenstate of energy and all the higher conservation laws. So these ij's are really quantum numbers that characterize the energy eigenstates, and I will use them as the quantum numbers in my study of statistics of matrix elements. Now, once I have these energy eigenstates, we can compute matrix elements numerically, which is what I will be talking about, because matrix elements in Lieb-Lininger have been known for quite a long time. So, for example, for the density operator, they were obtained by Nikita Slavnov in the late 80s. And so they have an explicit form. It's complicated, but they can be evaluated efficiently on a computer. Okay, so now, as I said, in order to study probability distribution functions of these matrix elements, I will use an organizing principle based on macrostates. So what are macrostates? These are simply families of energy eigenstates or microstates in a large volume that up to finite size corrections have the same densities of all conservation laws. And as we all know, so these macrostates are characterized by distribution functions. And these distribution functions, they basically tell me what are the numbers of integers in a given interval. And they're related in a very simple way to the usual root distribution function. So a macrostate is basically something that characterizes a family of microstates through the root distribution function. And what we therefore now will be doing in our computation of this probability distribution function of matrix elements is the following. We will choose a local operator, it can be the density or the Bose field or more complicated operators. So then we fix two macrostates. They can be thermal states. They can be thermal states at the same temperature, at different temperatures. They can be some of these atypical finite entropy states described by generalized Gibbs ensembles. All of these are allowed. But these I keep fixed. So then what I do is for these given macrostates, I sample corresponding microstates, so solutions of the Bethe-Ansatz equations. And this is done then by generating sets of these integers or half-odd integer numbers that correspond to the correct or pre-specified distribution functions rho 1, 2, and solve the Bethe-Ansatz equations. And then I solve the Bethe-Ansatz equations to obtain the rapidity variables. And once I have the rapidity variables for the two microstates, I use the exact expression for matrix elements, which I just flashed on a previous slide, to compute the matrix element numerically. Then I repeat these steps 3 and 4 many times to obtain a probability distribution function of these matrix elements, where now these microstates, EM and EN, are drawn from the basins of attraction of these two macrostates I started with. And how to sample these microstates is a bit complicated, and I don't have the time to explain it in detail, but if you're interested, you can ask me afterwards. Okay, so now let's come to results. First results is for diagonal matrix elements. So there I don't have a huge amount of new things to say. So diagonal matrix elements basically are just expectation values in an energy eigenstate characterized by these integer half-odd integer numbers J of a local operator, of a spatially local operator. And then it has been known for a very long time. I'm not even sure who was the first one to kind of say this clearly, but it certainly was known to Vladimir Korepin and his collaborators in the 80s that in a large volume, these diagonal matrix elements become up to finite size corrections, just functions of the root density or this distribution function that characterizes the macro state to which the microstate J belongs. And what we have done here by this numerical procedure I explained, we look at the probability distribution function, in particular the standard deviation of these diagonal matrix elements. If I compute this expectation value now with different J's drawn from the same macro state. And basically what you find is the standard deviation here in this plot. I show this for the interaction operator in the Lieb-Leninger model. In a thermal macrostate at temperature 10 and 3 different values of interaction strength. And what you see is the standard deviation as the system size becomes large kind of collapses to 0. Yeah. So it becomes very, very narrow. And so these fits to the numerical data are to polynomials where the leading term is 1 over square root of L. Okay, so this tells us about something, the probability distribution of these diagonal matrix elements, which collapses as L goes to infinity. So now things are much more interesting for the off-diagonal matrix elements. So there are basically 3 cases to consider here. So I can consider now the 2 microstates belonging to different macrostates, so being characterized by different distribution functions, rho. And there what we find is all matrix elements are not exponentially small in system size, but they scale like e to the minus L squared, with a coefficient that depends only on the distribution function of the macrostate, and that we basically can compute. Okay, so these matrix elements of microstates belonging to different macrostates are just incredibly small, e to the minus L squared. Now, matrix elements belonging to the same macrostate, which mostly from what I'm going to show you, we take to be thermal, but we have studied generalized Gibbs ensembles, looks like so. So typical matrix elements, yeah, they are not exponentially small, but they scale like e to the minus L log L, with system size, and then they have a subleading term which is exponential e to the minus ml, and this matrix M depends on the rapidities that corresponds to the 2 microstates, and this matrix M has a very interesting probability distribution function, which I'm going to show you on the next couple of slides. But all of these typical matrix elements are, again, not exponentially small, but they're smaller by this logarithmic factor. Okay? And finally, there are some rare matrix elements, very few of them, which are just exponentially small in system size up to power law corrections. Now, what I want to do next is basically show you the probability distribution of this subleading factor here, e to the minus m lambda mu L. Okay, so in various different examples. So interestingly, the probability distribution functions of these factors turns out to be essentially universal in some sense. So the first example I show you is I take as my local operator the Bose field, and I consider impenetrable bosons, okay, in a thermal state, temperature 10 and density 1. So in the plot here, I show the probability distribution of these m lambda mu's as a function of the value of m lambda mu itself. And I show this for different system sizes, 64, 128, 256, 512. And what you see is there's it's very good scaling collapse. So there seems to be a very nice limiting probability distribution function, which is fitted very well by a phenomenological fit to a Frechet extreme value statistics distribution function. And interestingly now, so if you go to the interacting case, so finite C and other observables, whichever ones you choose, they show very similar behavior. So they have this scaling collapse with regards to system size, and are also all well described by these Frechet distributions. So there seems to be some very interesting structure for typical matrix elements in microstates belonging to the same macrostate. Okay, however, now for practical purposes, the main upshot of what I've told you is that typical matrix elements are actually not relevant for, let's say, local correlation functions. And this can be very easily understood. So if you look at, let's say, a finite temperature dynamical two-point function of the Bose field, so J, take this to be a microstate corresponding to a thermal macrostate, then I can just insert a resolution of the identity between the two operators, get a Lehmann representation, which I've written here. Now, the number of states I have to sum over is essentially exponentially large because J is a thermal macrostate. So there is e to the L times the entropy density number of states. And as I've told you, if I take I to be a member of a different macrostate, which is not the same thermal state, matrix elements go like e to the minus L squared, so they cannot possibly contribute. So the only ones matrix element that can contribute is when the two microstates belong to the same macrostate. However, as I've told you, for typical matrix elements, the scaling of the matrix element goes like e to the minus L log L. But I only have an exponential number of states, which means typical states cannot contribute to the Lehmann representation. So then the question is, which states actually do contribute? And you can think about this a little bit. So an example is shown here for just the density operator. So if I fix J, this configuration of beta integers in the ket state, then the bra states that give rise to large matrix elements basically correspond to making a small number of particle hole excitations. Now, the number of these states, if you wish, just scales polynomial in system size if I put a high energy cutoff. So they again cannot contribute to the Lehmann representation. But then it turns out if you add soft modes, so make very slight rearrangements and a large number of them, matrix elements still are large, and it's those matrix elements which exhaust the Lehmann representation. Okay, so you can turn all of this in a practical procedure to actually compute finite temperature two-point function using a Metropolis Monte Carlo algorithm. So this is the finite temperature correlator I want to compute. This is the Lehmann representation I already had written before. And now basically what we do is we fix J to be a microstate corresponding to a thermal macrostate. And then we sample these microstates I now using Monte Carlo Metropolis update for single integer moves of this microstate I. And then basically what you find when you compute this two-point correlation function, the number of states that contributes to the Lehmann representation is basically shown here. So tau is some dimensionless temperature. S is the thermal entropy density of this thermal macrostate that we are sampling. And the number of microstates that contributes is shown here. So it basically tells you there are exponentially many in system size such states, but many fewer than there are thermal states. And that has to be because, as I told you, typical states don't contribute. Okay, so just finally, here are some results for actually the finite temperature dynamical correlation function. So this had not been computed before. Okay, so here are some results for larger, rather large systems. So L equals N equals 200, and here are plots for this two-point function of the Bose field in omega and Q space. So you do the Fourier transform for the full range of interaction strengths, temperatures, and densities. And you might ask, how good is this Monte Carlo algorithm? It turns out to be actually a lot more precise than I would have expected. So we benchmarked it in the impenetrable case against exact results that were known previously using a Freighton determinant representation. And the agreement is superb, actually. So this brings me to my summary, and I'm still in time, which is good. So what I wanted to say is the statistics of matrix elements in energy eigenstates of integral models has a rich and interesting structure. The main message is, unlike in generic models, the dynamics of local observables is governed not by typical states, but by exponentially many rare states. So all I've shown you here were basically numerical results. Of course, it would be very nice to obtain analytic results. In the second part of the talk, I showed you how to sample these exponentially many rare states using Metropolis algorithm, which allowed us to get some new results for dynamical two-point functions at finite temperature of the Bose field. And what we're thinking about now is generalizations of this Monte Carlo sampling method to quantum quenches and endpoint functions. And there, really, the key issue or question is whether there is a Monte Carlo sign problem. And I have nothing to say about that yet. And with this, I thank you for your attention.
Fabian, hello. It's me, Andreas. I have a question of matrix elements you calculate for the rare states. You construct the rare states by doing some finite changes in the occupation of these positions of the momentum, let's say slots. And when there are many small changes.
Exactly. So exactly? You're absolutely right. So this is how the Monte Carlo algorithm works. So you have Monte Carlo time. And in every Monte Carlo step, you change one integer. Yeah. Using a Metropolis algorithm. But then, of course, the Monte Carlo time is very long. Yeah. And then at initial times, you're not sampling the right states, but then eventually you hit the right basin of attraction, so to speak, and you start sampling really these exponentially many rare states.
I see. And how much do these matrix elements fluctuate? Maybe they can be replaced by just some mean value.
Yeah, okay. We have some results on that. I think that would be too simple. I mean, the fluctuations are indeed kind of not enormous, but I don't think you can just replace them by an average and still get the full dynamics.
Okay, thanks.
Can I make a question? Can I ask?
Please.
Of course.
Ciao, Fabian.
Ciao.
Look, can you do the same exercise with form factor of continuous theory? Because there you have a ample set to test.
Sinch Gordon, Giuseppe. I can do Sinch Gordon.
You do?
But I can do it. So the reason we have stuck to Lieb-Leninger is when you have strings, doing the numerics, the numerical part becomes a lot more difficult because the strings for large L, they sit exponentially close to poles of the matrix element. And then the computation of the matrix element becomes computationally very expensive. But Sinch Gordon, yes, absolutely.
Okay, thanks.
Maybe ask a naive question. So if you have a system, you don't know integrable or not integrable, given the states, could you tell by your statistics that it is integrable or not?
Yes, I could. Yes, I could. Yes, I could, but there is a caveat. So if your system is very small, if it's a many particle system, let's say a spin system, you should be able to do more than 8 sites or something like this, right? I mean, the system shouldn't be too small. Then you can.
So 10 sites, is it good?
Okay, so okay, you're always difficult to satisfy. So the smaller L, the more difficult it becomes to tell the difference. So 10 might be enough. So 20 probably would be enough.
No, 20 is more difficult, but let's say 14 sites. So
probably, I think so. 14 is probably enough.
Any more questions? In that case, we thank the speaker again.